Okay, so welcome back to another video. So here we have a nice algebra problem that's a short yet interesting one. So we have that ln of x divided by y minus z is equal to ln of y divided by z minus x, which is equal to ln of z divided by x minus y. So what is the product of x to the power x times y to the power y times z to the power z? And I should also mention that x, y, z for our variable, they should be strictly greater than 0 for the reals, since we have a natural log function that's strictly increasing. So to give a little bit of a short outline, that all we need to do is that if we're given these three different equations and they're set equal to each other for the equality, so they have to equal some sort of value that we can actually, define as a variable. So all we have to do is figure out a way of how we can convert what is given such that we convert it as a form of a second order tetration power, tetration being a exponential tower of finite order. Here this is 2, since x to the power x, y to the power y, and z to the power z. So pretty straightforward from there. So a little bit of creativity using some algebra there, that we just have to convert this from here to here, and it follows with a bunch of, exponential functions. Well, not a bunch, but one step follows with the exponential function specifically. And so with that, let's actually just jump right in. So we're given these three equations. So as I said that we should set this equal to some value. So let me first write this out. So ln of x and then ln of y, and then set this equal to ln of z with the denominators, of course. We'll call this value k. Now, what we're going to do is to do a little bit of nice creativity over here. I don't know why I wrote equal signs over here by mistake. So what I'm going to do is I'm actually going to multiply and divide an x, multiply and divide a y, and multiply and divide a z to each of the respective equations. And that should be helpful since we want to get this in the form of a tetration for x to the power x, y to the power y, and then z to the power z. So, because if by doing so, that means if I multiply x, then applying the natural log properties, I'll put that as the exponent, but I'll have to multiply the x to whatever the product with the denominator is. So to keep things straightforward, so now I have ln of x to the power x, and then divided by x times y minus x times z. Set this equal to ln of y to the power y, then divided by y times z, subtract x times y, or y times x, whichever you want to look at it. Commutativity, so it's nice. And so now I have ln of z to the power z, and then that's set that, then z distribute over here, so it's x times z, and then minus y times z. And so that's still equal to k. So now what I can do is, so everything is set equal to each other, so one by one, I can actually get the natural log by itself by multiplying by the denominator over here, and then take the exponential of both sides. So in other words, I have, this is x to the power x, which of course this is just equal to e to the power k, and then just multiply with x, y minus xz to k, and then do this each time for separately. So that means now I have x times y minus x times z. Then next, I'm going to move on to y to the power y. So do the same thing. So that's e to the power k, and then multiply over here back to there. So that means this is y times z, and then minus x times y. Then do that one more time for z to the power z. And so that's just equal to e to the power k, and then multiplied, so k times over here, so x times z minus y times z. Okay, so pretty much all that's left now, let's actually now multiply everything together. So x to the power x, and y to the power y, and then z to the power z. So put everything back in together, and then put in that substitution. So I have e to the power k times x, y minus x times z, then times this with e to the power k, y times z minus x times y, and then multiply with e to the power k, multiply by x times z, and then minus y times z. With exponentiations with the properties, I can actually just add the exponents together. Not only that, everything shares a k, so I can actually factor out the k to that. So that means I have e to the power k, then multiply with x times y minus x times z, add this with yz, then minus x times y, and then add this with x times z, and then minus y times z. And then you'll notice that we're actually going to have some terms that cancel out. So you'll see xy is canceled, then over here, then xz is canceled, and then yz is canceled. And so therefore that leaves with just e to the power k times 0, aka just e to the power 0, which is just equal to 1. So therefore that actually completes the final answer of our value, x to the power x y to the power y and then z to the power z, the titration of those products, is indeed just equal to just the number 1. And so therefore that actually completes the value of this short, yet interesting algebraic problem with a little bit of creativity using properties of the natural logs. I just hit my doorstopper by mistake. So there you have it. So yeah, that's pretty cool if you ask me.